3.12 Photoelectric Effect. We're going to be talking about waves and IMF forces and how they're being affected using light, electromagnetic spectrum, atomic emission spectrums, and quantum theory. So let's talk about a wave real quick. A wave is considered to be, it could be in the light or any sort of liquid, and the distance between the two peaks is considered to be the wavelength. That usually is going to be determined by the unit lambda or wavelength. Here we have two types of frequency wave. We have a low frequency wave and a high frequency wave. High frequency wave are generally more energetic and they have a shorter wavelength, while a lower frequency wave is slower and has a longer wavelength. And the way we represent frequency is with V, the number of times a wave repeats itself per second. So in the high frequency wave we have more peaks than the low one. The formula for determining wavelength and frequency is equal to C equals lambda times V, which is the speed of light 3 times 10 to the 8th meters per second equals to lambda times V, or the frequency expressed as hertz and wavelength as meters. So let's do a couple of problems here. I want you to pause the video and go ahead and calculate the frequency of a green light that has a wavelength of 545 nanometers. So we first are going to use the equation C equals lambda times V. We rearranged the V and it's going to equal to C over lambda. Because we already know C as a constant and lambda is given, it's all a matter of a simple division. So in this case, we're going to divide 3.00 times 10 to the 8th power meters per second divided by 545 times 10 to the negative 9 meters. That's already been converting off the nanometer. And your answer is 5.50 times 10 to the 14th hertz. And keep in mind, it is 3 significant figures. Now let's talk about the theory behind the photoelectric effect, and specifically the quantum theory and Planck. So Max Planck hypothesized that energy radiated from a heated object, such as a stove element or a light bulb filament, is emitted in discrete units or called quanta. And I want you to think about this in terms of light. So if I take a light and I heat it up, it's going to radiate some sort of energy, because as that energy starts being absorbed by that filament, eventually it will release that. And that's usually how we find things like light bulbs, lasers, things like that. And so let's talk a little bit about Planck and quantum theory. So if we take a look at energy and if we increase the intensity, energy should also increase. And so we assume that the energy increases in a continuous stream. However, that's not really the case. The way it works is that energy is actually increasing, but in these very specific or discrete units. And they're usually by a full quantum or not at all. So there's no half quantums or fractional quantums. Now the quantum is referred to as the steps of how much energy you have for each one. So if you're increasing intensity, you're going to jump by each of those steps, and is equal to the energy for a very specific frequency of that radiation. So in other words, for you to jump quantum, you're going to have to be able to figure out the frequency of that specific electromagnetic radiation. So Planck's constant is basically going to be h. So if we rearrange the equation and we take a look at how much energy you're taking to jump per each of these steps, you're going to multiply it by Planck's constant, which is 6.63 times 10 to the negative 34 joules per second, and you multiply that by the frequency over s minus 1. And that should tell you approximately what the energy level you're going to need to be able to jump electrons. This actually falls under this very basic idea called the photoelectric effect. The photoelectric effect basically is, the world knew that if you take a clean metal and it could actually shed these electrons, if only you could give specific frequencies of light. So if I give you, for example, a metal plate and I increase, let's say we put some sort of light or energy through it, the metal plate's going to actually emit these electrons, and you're going to be able to measure it via this called collector plate. And based off that, you should be able to figure out what frequency of light this metal ejects. So the first fact is that highly intense low frequency light does not eject any electrons. So if you think about everyday light that we have, like white light as an example, even if it shines on it, it doesn't eject it. So if I put on that one, the light won't turn on. And the way we detect it is that once it hits this collector plate and we put this energy in, the lamp will actually use the light being generated from this metal plate to the collector plate to turn that lamp on. However, a second fact is that when you've reached a threshold frequency, the electrons are going to eject immediately, and then the lamp is going to turn on. So if I go ahead and turn this power on, the electrons are going to get ejected, and then you're going to get that specific light. Interestingly enough, by increasing the intensity of the light of the frequency, it's going to cause electrons to eject at a much higher rate. So if I try to eject this by increasing that intensity, the light's going to turn on, and then the current's going to increase by a much higher velocity. So the whole point of this is to understand the fact that these quantas are going to be able to move if you give the right intensity and the right frequency. The fourth fact is by increasing the frequency of the light, it also will increase the velocity of the ejected electrons. However, all the ejected electrons will share the same velocity. So normally you're not only going to get a brighter light, but you're also going to turn on a lamp that is much quicker to turn. So again, when you're changing that frequency, you're increasing that energy, you're going to be increasing that velocity of those ejected electrons. So that brings us to Einstein's theory of 1905, talking about this beam of light called photons. And so light can actually exist as two ways, as a wave and as a photon. And the energy of the photon is related to its frequency. So if I multiply by Planck's constant, you're basically going to be able to figure out how much energy you have. So obviously the higher that frequency is, the higher the energy you're going to get. And the quantum of Planck is a particle called a photon, which gets ejected. And if the frequency of a photon is below a certain threshold, no electrons are ejected. So it has to be within a very specific frequency in order for that electron to move. If the frequency of the photon is at or above a certain threshold, its energy is transferred to that electron. And this causes the electron to overcome the forces of attracting and holding onto the metal. So I want you guys to think of metals having these sea of electrons. And these sea of electrons are going to be holding these electrons together. But once you give enough light to it, the electron's going to absorb that light energy, and then it's going to eject it. And then the electron's going to absorb that photon. So again, going back to Planck and Einstein. So if we combine both together and we take a look at Planck and Einstein's photoelectric effect, you can kind of see that, again, we're using that equation of E equals hv. Now, you're also aware of Einstein's famous energy equation, which is energy E equals mc squared, which multiplies the mass multiplied by the speed of light. And that brings us to, the electromagnetic spectrum. So you already know that the higher energy waves are located on the left-hand side. So specifically X-rays, UVs, and gamma rays. On the right side, you're going to see the lower energy waves like infrared, microwaves, and radio waves. And you can kind of see that the visible light is between a very specific range. And so if you think about it for a second, specific types of frequencies will definitely generate higher energy spectrums. So here's a classic example of atomic emission spectrums, where I shine a light and then it hits a prism, and then we take a look at the screen. Once the light comes in, the prism is going to split the light into very distinct frequencies or wavelengths. And there we can tell, based off the color, which frequencies have higher energy, what colors have higher energy. And to give you an idea with this is that if you take a look at hydrogen emits specific lights. It can come out in 4 different colors with specific wavelengths and obviously with specific frequencies. So every element has its own identity in terms of what it's composed of based off of these electrons. And so the question is, why do we have different colors of light? And the reason why is because with the different changes in frequency and wavelength, color is going to change. And so light can exist as a duality, as a wave and as a particle or a photon. And as the wavelength and the frequency changes, the energy per photon will also change. So think about it for a second in terms of how to make atomic light spectrum. So if I have an atom and it has different rings on it, N1, N2, N3, and 4, and I want to know what type of light you produce, what I try to do is figure out how much energy you need per jump. So I'm going from N1 to N2 or from N2 to N1. You're beginning to see that in order to do that, you're going to need some sort of energy put in. And the moment you jump at different levels, you're going to be emitting a certain specific type of light. So if I jump from my N1 to an N4, or from an N4 to N1, it's going to have probably a higher frequency since it's a higher energy orbital, and so on. And so as you can see from here, you basically get these different jumps between these quantas, and that's what gives you the ability to detect different types of light. So when a photon is absorbed by an atom, an electron moves up or down the energy levels, and an increase in that energy is equal to the energy of the photon that it was released. So if I give you level 1 and I want to jump to level 3, I have to give you the actual amount in order to jump that amount. And so the increasing in energy is also equal to the difference between the two energy levels. So whatever that energy level is, that's the amount of energy I need to jump. When they emit, once the electron hits that certain level, it's going to drop and it's going to decrease back to its original ring where it was, and that's going to emit a specific type of energy, and that's how we see light. Alright guys, well hopefully you enjoyed this. This is more about just reviewing a little bit about light spectra and what causes different colored lights depending on how electrons get ejected using Planck's constant and also Einstein's photoelectric effect.